Thanks, Avi. So this is a talk about the analysis of reasoning based on statistical data. It's going to be for the analysis of applications of machine learning. Okay. So what I want to do is provide a principled alternative to unsupervised learning by sort of placing it in this context of a larger application, right? But in the first place, I have this PAC Semantics thing prominently displayed in the title, and I want to explain to you what this PAC Semantics is and why we need something like it. So start off with this story. It may seem silly at first, but don't laugh. Something like this could be happening somewhere in the world right now.
After talking to aliens, you can't.
No. You just wait. You just wait. Okay. So imagine that you're a consultant who's been hired to determine whether or not the birds of an aviary fly. Okay. And you're given this feeding log, this partial sample of a feeding log, saying which birds ate what on some day.
What are you trying to determine?
You want to determine whether or not the birds of this aviary fly based on what they ate, right? You also have some other knowledge about the birds of the aviary, right? You know that everything but penguins are flying here, and the penguins eat fish, okay? Now, obviously, the actual data you have here doesn't tell you anything about whether or not the birds are flying, directly. And those rules you have over there also aren't enough to determine whether or not the birds are flying, okay? But what you can do is you do some sort of statistics on your data, and you determine, in this sample, the birds are not eating fish, something like this, okay? And given that as a additional assertion, you can derive that the birds are flying. Okay. So you get paid as the consultant, but what's the problem here, right? What's wrong? The first clue that there's anything wrong is this kind of p-value or what have you. The kinds of conclusions or rules you can derive from some sort of statistics don't hold with certainty, okay? What that means is, sort of this premise is not strictly true in some sense, and therefore you can't really say that the conclusion is true either. Just because on some sample the birds weren't eating fish doesn't mean that there aren't some penguins out there that you missed, okay? And the root of this problem traces back to the kind of guarantees you get from things like PAC Learning. Okay, so I'm going to review, yeah.
So when you're drawing conclusions, you have to draw conclusions about the whole corpus of data or individual points of the data?
So we want to draw conclusions about the corpus or source of the data, right? We're thinking of each individual data point as just some example. Very, very much like in PAC Learning,
okay.
Right? So yeah, so I'm going to review the definition of PAC Learning for those of you who are maybe not so familiar with it or forgotten it. There's some arbitrary distribution out here, D, okay, that produces examples. So there's these n bits with a label bit in PAC Learning, okay, and you get a bunch of these. Okay, you feed these to your algorithm, which spits out a representation of another Boolean function. Okay, what is this function? Well, if these labels for your examples are actually produced by some function C of those first n bits, coming from a concept class script C that your algorithm has been designed for, like a conjunction over these bits or a decision tree over these bits or something like this. Okay, if these label bits have actually been computed by such a rule, then with high probability over you having gotten a good set of examples from D, the function you produce on a new example from D with high probability is going to predict what these label bits are. Okay? So that's the guarantee you get from PAC Learning, right? And so now the conflict that you run into if you're trying to, trying to reason with these rules is this. So you're treating these things as though they were actual facts. Like in information extraction, for example, people will actually take some sort of a rule that that seems to be true on some sample, and then assert it as being like a true thing, and add it to some sort of a rule base. Okay, and this actually happens in applications. But okay, so I can write this this prediction rule equals my label bit as some sort of like a formal logical statement. But what happens if you really take that seriously? Well, I mean, you're only guaranteed that the function is predicting the label on a 1 minus epsilon fraction of the domain under the distribution, right? So there's still some epsilon probability that this thing is false under the distribution potentially, and so this rule is not valid in Tarski's sense, in the usual sense of mathematical logic, right? But nevertheless, there was some sort of utility to having a prediction rule like this, right? I mean, there are reasons why people use machine learning algorithms, and it's not captured by this sense. So, need for a PAC semantics or something like it is motivated by this kind of conflict.
Well, I mean, this kind of conflict is not new, and not because of, and also before PAC, people studied probabilistic reasoning for lots of other without PAC. So when
well, I mean,
what you know is not certain. So you're going to review any of this, or in what sense what you suggest is different, or you are going to?
So it's okay. I mean, this was a motivation for introducing a particular kind of semantics, right? A particular distribution semantics. I'm not claiming that this is new to my work. So Les had a paper on robust logics where he, fixed a particular semantics. And so I'm just reviewing the motivation for that, which is going to be our starting point for today.
Yeah, I understand. I'm just saying that this probabilistic reasoning volume, not related to PAC at all, not related to PAC, about what do you do with rules that are not 100% certain?
Right.
They wrote books on it. You are not compared. You will not tell us how is it different, or how is it better.
Well, in fact, I think it fits in. Okay, well, no, I will say a few words about it. I will say a few words, not too much. Well, yeah, okay, right now. So, right, people had talked about one thing in particular that you might be familiar with are, Halpern had these probability logics. And they're actually strictly richer than what we're going to work with, right? Because this was logics with the form, I have some formula phi, and I can assert that it's holding with some probability at least p, okay? And, in some sense, what we have in our semantics is there might be some, external to the logic, this 1 minus epsilon, right? And so there's just these formulas, and we're saying, oh, they're holding with probability 1 minus epsilon, but we don't really reason about the epsilons or anything like that, okay?
So in some sense, you only consider the situation where epsilon is negligible?
Not so much where it's negligible, but it's more to say that, I mean, no, epsilon can even be a constant. So it ultimately will be sort of like a free parameter, which you can fix in your applications. What I want to say, though, is that we're not treating reasoning about the epsilons as part of the logic, in particular, okay? So the problem with probability logic is that because it's, everything in logic then plus also having this like second sort where you can reason about probabilities, things are just getting harder. And our objective here is to take some more limited thing and show that you can develop more efficient algorithms for it. Okay.
I just wonder if in all these other, like these probabilistic logics, and there are others, if you did treat the epsilon as a free parameter, like in non-standard analysis, something that you can add up any number of times you're going to do inferences, then whether they're logic just in this special case, then you don't have to reason. If you know that you're chaining, like with the example, if you are chaining rules at most 100 times, and epsilon was at most 1 over a million, forget about it.
In those cases, you could, yeah.
So even in these logics, you don't have to reason about it if you knew a bound.
If you had such a small bound,
such
yeah.
a small, which I assume you are using.
Well, for us, really, we'll want to treat epsilon as some sort of not quite negligible parameter. It'll be well, crucial for it to be really interesting is that we'll try to handle cases where epsilon is actually something noticeable, and we'll be able to tolerate some counterexamples. But that means that we do have to be careful about how exactly we set it up, right? Yeah. So there's one other contemporary example of a thing that people use now, which is these things based on graphical models in machine learning. Right. So these things like Markov logic. So ultimately, there's some sort of model of a graphical model of a distribution, and they associate some logical semantics with it, and they can do some reasoning, things like this. And the problem with these things is that they don't really solve the learning problem that we want to solve, right? There's this thing they call the structural learning problem. Graphical model is that somehow your variables are nodes, and dependencies between the variables are edges. And if nobody hands you that network of dependencies, it's not known to be easy to learn. It seems like it's hard to learn because it's effectively sort of like density estimation. It's just there's some small promise there. Okay, so anyway, that's why what we do is distinct from that. And yeah, so as I said previously, this is some weak standard, some weak semantics. It still captures the kinds of statements you get out of PAC Learning. Will allow you to draw some, do some inference, draw some conclusions from such statements, and is going to allow you to design more efficient algorithms. Okay, so here's the main definition now coming up for propositional logic, called propositional variables, Boolean connectives. So we have a background probability distribution D over assignments to your propositional variables. Okay. And here's the main definition. Phi is 1 minus epsilon valid under D. The probability under an assignment drawn from D that phi is satisfied is at least 1 minus epsilon. Right. So yeah, these are 1 minus epsilon valid things are like rules of thumb. There may even be noticeable counterexamples to them, but they're still mostly true as long as epsilon is sufficiently small. Okay. And that's sufficient to capture the kind of confidence interval thing that you get when you are, say, looking at some finite sample and saying, oh, well, here none of the birds ate fish, then, you're concluding from that with high probability a 1 minus epsilon fraction didn't, and so therefore 1 minus epsilon fraction are flying, right? Another upshot of this kind of a definition is that it also would allow you to be sloppy a little bit in this background knowledge. So for example, this rule about the penguins being the only non-flying birds, well, if there were some emus out there, but they were relatively rare, then this might also hold for a 99% fraction of the birds in the aviary, say. And in that case, by taking a union bound over the failure probability of these rules, then for some slightly smaller epsilon, you could also conclude that, say, maybe then with 98% of the birds are flying. Something like this, okay?
So high probability means over the randomness of drawing samples?
Yeah, over the distribution, right? We're only reasoning about properties of the distribution here. Good. Right. Okay. So, right, I said a little bit about what PAC semantics is for us, and now I'm going to get into the algorithmic problem that we want to solve, or problems. Okay. So, in this data mining story I told you, the setup is a little like this. You have some data set given by these examples drawn from that common background distribution. And then either some algorithm or some data scientist takes these rules and feeds them to an algorithm and produces some sort of rules that are holding over the data set. Maybe they've run a regression and said, oh, there's some linear relationship between some of these variables, something like this. Okay. Typically, one would take these rules as being the summary of these interesting facts about the data, And then you draw some conclusions about this. You know, do I want to invest in vinyl ponchos? I don't know, something like that.
So just a second. I mean, most learning algorithms we are familiar with don't produce rules.
They produce
classifiers.
Yes. However, a classifier gives you a rule in the sense I described earlier, that it's some so like for example, suppose it's learning conjunctions, right? And that gives you a rule of the form, this conjunction equals label bit, right? And so that's a relation that's holding.
A rule is now a function.
Yeah, a rule is a Boolean function always, right? Exactly. Okay. So yeah, you take these rules, you have a query, say, and then now we want to decide if this query is following from these rules. Okay, so this is you think of like a theorem proving or logical reasoning problem.
Actually, I still have a question.
Yep.
I'm not completely happy with this answer that the rules are functions. What are the variables? So when we learn conjunction,
Mm-hmm.
the variables are
These attributes, yeah.
different attributes of something.
Mm-hmm.
They are not like penguins necessarily. I mean, we don't.
Yeah, you
have
would.
an assignment to them. This is penguin. This is fly.
But what you do typically is,
So how do
in
you
such a
get-
case, you have these extended literals, right? Which are of the form, this variable from some larger class takes one of several different values. So you have a literal, this first bird is a penguin, first bird is a emu, first bird is a finch, I don't know, whatever. Maybe you have some rules saying these are mutually exclusive, some small set of rules describing those constraints, okay? And those mutually exclusive rules are given as typically maybe some sort of background knowledge. If we're talking about resolution or something, that's a bunch of clauses you add in. But then, yeah, you just have this, then ultimately a Boolean encoding of, which type of bird you've got, right? One of these things, which is the type of bird that ith bird actually is going to be true, the rest are false.
So are we assuming any, for this second problem, are we assuming any structure on the rules? Are there extended variables or everything you say is independent of that?
So it'll be, right now I'm just assuming we're working with these Boolean propositional variables, right? I did have a slide about dealing with first order logic that has this transformation where you are working, there are atomic formulas in that case, right? But that's effectively the same thing. Right. Okay. So this is this setup that you would typically have when you're doing something like data mining. Right? And so what we're doing here instead is we're sticking these two stages together, saying, well, okay, what if I take the examples and the query I want to answer directly and then come to a verdict on it? Okay. And the reason I am putting these things together as opposed to trying to do some sort of like standalone, let me extract everything I can about the data, is that it's going to allow me to guarantee some kind of completeness condition for the rules.
Is the query also Boolean?
The query, yes, is also some sort of a propositional formula for us.
It's a Boolean function.
Yeah.
So, if you want to know just whether a formula is true in general,
Mm-hmm.
the type of it over the input, you just evaluate it over the sample.
Yeah, so the complete information setting here is trivial, which strongly suggests that ultimately we will not be studying a complete information setting. But I'm getting there. I'm just taking my time.
In this seminar.
Yeah, so, right, this is the problem we want to solve. As Avi's pointed out, in complete information setting, it's trivial. And I'll deal with that in a second. But, I just want to suggest to you that this is actually a useful thing to solve. Like, for example, if I want to, design policies in some setting, then like a branch of a decision tree, might be encoded by, given that these attributes are holding along the branch, and given that I take these actions along the branch, I have some goal outcome I want at the end, and I can use this to try to, say, construct this decision tree policy branch by branch, for example, okay? this query evaluation problem is maybe a little more versatile than it looks at first. In any case, right? So the kind of completeness theorem that we're angling for looks something like this, with a bunch of scare quotes that have to be erased in the next 30 minutes. So for every natural tractable proof system, we can develop an algorithm that's simulating access to all the rules that can be verified 1 minus epsilon valid on examples when we're searching for proofs in that tractable proof system. Okay. I haven't defined most of the terms I need here. I'm just trying to give you some idea of what the final theorem, well, what the theorems we prove are going to look like. Okay. And so it's completeness in this sense with respect to these, rules that we could mine from the data. Right, so full information is easy. Plug in polynomial size sample and evaluate, and that gives you a good estimate of the validity of the formula. But, as I suggested, in most situations where you would actually care to do some sort of reasoning, you don't have complete information. Okay, and back in our silly story, recall that I mentioned that by looking at this data, you couldn't tell whether or not the birds were flying. Okay. I know.
It never happens. It's only completely epsilon.
Unfortunately, in this talk, epsilon is non-negligible. Right, so these attributes are not present in your data set. And so I claim the way you should be thinking about it is there's going to be some distribution that's actually assigning values to all of these attributes, but you don't get to see all of them. You only get to see some of them are missing. Okay. So generally, the methods we're going to propose are going to be useful in situations where you're missing some data, maybe it's hard to collect or not collected, and there is some background knowledge that somehow is relating what you've observed to what you didn't observe, or maybe your query mentions both. Okay, and so somehow you have to deal with this missing data.
But
So algorithms are tailored to the query. They are not like something, so like the two-stage reasoning, the two-stage algorithm that you had, you first produce a learning algorithm, and then it's conceivable that once you have this hypothesis, which is only 1 minus epsilon accurate, you will assume that to be 100% accurate, and then you will just evaluate the query based on that hypothesis. You will never look at the data again.
In those cases,
In those cases. And what seems to be a difference is that in this combined way of constructing this algorithm, every algorithm is designed specific to the query. So there may not be any intermediate hypothesis here.
Potentially there may not be, yeah, in particular. But nevertheless, we would like to guarantee that, in some sense, if there were intermediate hypotheses that would be useful, then we behave as well as if we had discovered them.
the missing attributes are known. I mean, are they
Yes.
named?
Well, they'll be mentioned in your query or something. I mean, if it's some missing attribute that's not mentioned in the background knowledge of the query, then it's not going to be relevant.
Okay, so it's mentioned in your query, but you have the mapping between the names of the attributes in the query and the attributes in the data samples.
Yes, we assume that.
You assume that. Okay.
We assume that. Okay, well, anyway. So, right. Let me talk more about our model of partial information right now. Okay, so it's going to be given by these masking processes. So yes, I mean, our examples, we think of our examples as just being 3-valued, where some of the attributes are just these missing Boolean values. Okay. So a masking function takes a complete assignment and maps it to a masked example by hiding some of the entries. Right. And so a masking process is just a masking function valued random variable. And so in particular, this is going to allow us to, if we choose, to consider cases where which values are hidden is correlated with what the underlying complete example is. So maybe when this attribute is true, it always gets knocked out, something like this. It doesn't have to be that way. So, you know, and of course, an interesting natural example of a masking process is this, you know, biased coin masking, where you just are tossing this mu biased coin for each attribute. If it comes up heads, you let it through, and if it's tails, you knock it out. And this, of course, has appeared in many places, you know, starting with models of partial information learning to this population recovery problem, and many other works in between in some sense. Okay. In the final part of the talk, I'll come back to this masking process if we have time. But for now, let me stick with the arbitrary ones. Okay. So generally, our setup is like this. There's these two distributions, one over examples, one over masking functions. Okay. For each example you get, you draw a fresh, you know, assignment from D, draw a fresh mask from the masking process, and what you get is this partial assignment. That's the evaluation of my masking function on that assignment. Right. So each time your algorithm gets an example, it's one of these partial examples, right? But I'm still defining this, you know, validity with respect to that underlying distribution over complete examples. Okay, good. So, right. And these
The masking process is least independent of D, even though you put the action of the outcome on
yes.
the example.
Yes. Okay. So on to these algorithms for learning and reasoning. So if you're designing an algorithm for reasoning, I claim that you want it to be complete for some sort of fragment, which is going to allow you to evaluate the relative power and so on of these algorithms. And what I mean by that is, okay, let's consider this well-known fragment of resolution. Just to remind you, it's a proof system for refuting CNFs. You treat your CNF as some initial set of clauses, and then given a set of clauses, you can derive new clauses either by weakening, which is taking a clause from the set and adding literals to it, or by this cut rule, which takes two clauses with the variable and its negation mentioned in them, tearing out the complementary pair and taking the or of the rest of those literals. And so that's just, you know, if there's a satisfying assignment to your original set of clauses, X couldn't be satisfying both of these, so it must also satisfy this. And now if you derive the unsatisfiable empty clause, then since these preserve satisfying assignments, the original set of clauses could not have been satisfiable in that case, right? So resolution is nice because it has these, you know, tractable fragments. So bounded width resolution, where you only mention a constant number of literals per clause, you can decide whether or not there's such a proof by dynamic programming of the, you know, where your table just contains whether or not you could derive these clauses, right? It's a polynomial size table. But likewise, there's this tree-like bounded clause space fragment. Tree-like proof, you just can't reuse intermediate derivations. Bounded clause space is just, you imagine that you have some working set where you can only use clauses in the working set for your derivations. It has constant size, and if you can, without reusing things, using this, you know, constant size working set to derive your proof, then likewise you can search for such proofs in polynomial time depending on the size of your working set. Okay. Right, so our basic strategy is, okay, well, since resolution is sound, when there's a proof of our query from some other 1 minus epsilon valid CNF psi, then phi is 1 minus epsilon valid, right? Psi implies phi. If it has weight 1 minus epsilon, so does phi. Okay. And that's useful if psi is somehow easier to test for being 1 minus epsilon valid using our partial examples. Okay. So this is our definition. We'll say psi is 1 minus epsilon testable under this distribution over partial masked examples now. If the probability under you know, a masked example drawn from this distribution that the restriction of psi simplifies to constant true, where really, okay, you know restrictions are plugging in the values for variables, and that gives you a formula on the unknown variables. I guess crucially here, I mean this local simplification rule, where I just recursively simplify gate by gate. I don't do some non-local thing. Okay, so if the restriction of psi is simplifying to the constant true is probability at least 1 minus epsilon, I'm saying it's 1 minus epsilon testable. And so this is something that I can compute in linear time. But also in some standard cases where it's tractable to decide whether or not psi is a tautology, like CNFs or intersections of half spaces, this is equivalent to psi being a tautology given the partial information in rho. Okay, 2 DNFs are a counterexample. Fine. Yeah, okay. The observation is that, so if psi is a CNF, say, okay, you can decide whether or not a CNF is a tautology easily, right? I mean, because as long as the clause doesn't contain a complementary pair, it could be falsified. And so, given this partial information in this masked example rho, you plug in some of those values. If the entire CNF is not simplifying to this constant true everywhere, then there still is some extension of that masked assignment that falsifies it, right? Right. So that's what I'm claiming, basically. But this is something that still I can compute in linear time, even if it's like, say, a 3 DNF, and there's no way I can hope to try to decide whether or not a 3 DNF is a tautology efficiently. Right. Okay. So what I want is to guarantee some kind of completeness with respect to these testable formulas, right?
So how do you do it for DNF?
Oh, well, I plug in the restriction. And if the 3 DNF is simplifying to the constant true, right, that means that, for one of these terms of the 3 DNF, everything was satisfied. No, because I'm just doing this local simplification, right? So this bit about the local simplification is what I really mean. So write out my 3 DNF as a tree, right, and then just sort of node by node, I do some sort of simplification. It doesn't, look across the different nodes.
So it's not about whether it's a tautology, it's just about whether it
simplifies under that partial information. Exactly. Right, and it's just in those other simple cases that it turns out to be equivalent to tautology. Yeah, in general it's not. Yeah.
You don't just given partial assignment.
Right, exactly. But this is some definition that is very efficient to compute. This is a syntactic simplification. Okay. Good. So I want to guarantee completeness with respect to these, easy to evaluate, things that are easy to test that they're true. Okay, and completeness when they complete a proof of my query in some tractable fragment. Okay, right, and so as I was saying, in analogy to these rules that this, learning algorithm blindly produces in this 2-stage version, I'm saying, okay, well, I can match, any set of rules as long as they're testable over here. Okay, right, so the actual theorem that we're going to get looks more like this. There's still a little bit missing, but so we're going to solve the following promise problem. Okay, we're given this query phi and access to these masked examples, and we distinguish queries that are not 1 minus epsilon valid from queries where there exists some testable premise formula psi, where there also exists a proof of the query phi from this testable psi in our tractable fragment. Okay, right, so I'm guaranteeing in this sense completeness with respect to the testable formulas. And yeah, and in particular, if I'm allowing epsilon to be something even noticeable, then this means that somehow I need to do this in a way that's robust to some counterexamples potentially. And so that's a little like agnostic learning, but it's easier here, and perhaps we'll see why. Okay. So the main trick that we use here is that these tractable fragments have this nice property. If you take the same restriction and apply it to every step of the proofs of this form, you get a proof of the same form, right? And if the original proof is a refutation of a query phi, then the restriction is a refutation of restriction of phi. Okay, so bounded width resolution, for example, I hit every step with the same restriction, it turns out that what you get is still a resolution proof. And clearly it's bounded width because, you know, if I plug in some of the variables and simplify, then the width doesn't get any wider, doesn't get any greater. Similarly, it's true for this trivially bounded clause space. You know, there's a little bit to think about there, but it's not hard. So this suggests the following algorithm, right? So I'm given my query DNF and this set of masked examples, and I just iterate over them, plugging them into the query one by one and searching for a proof. And if I succeed in a 1 minus epsilon fraction, I accept, and otherwise I reject.
Given a DNF, this DNF, what we are going to test, that's a query.
Yes.
It's in DNF form.
In this case, for resolution, yeah. These are my masked examples.
These are the examples.
Mm-hmm. It's very simple. And the reason why it works, right, well, okay, I can include background knowledge. It's easy. The reason why it works is, look, so resolution is sound. If you have a proof of this restriction of phi, it's a tautology. So whatever those missing values were, they had to satisfy phi originally, right? So if phi was not 1 minus epsilon, okay, minus gamma valid, then with high probability, 1 minus epsilon fraction of those, you know, underlying examples did not satisfy phi, and so therefore these restrictions could not have been tautologies, and then you cannot have found resolution proofs of them in 1 minus epsilon fraction. So in the first case, you reject with high probability if you give me this slack factor.
So where does the slack factor come in?
So I'm introducing it to both sides of the promise now, right? I'm making my decision at 1 minus epsilon, but I need a little slack above and below, and that's what's going to control my sample complexity, actually.
So the 1 minus epsilon was over the sample size.
It is also. So it's 1 minus epsilon, so minus gamma versus 1 minus epsilon plus gamma is what I'm actually going to be distinguishing. I need some gap there. Okay. Right. So, but this is the analysis for the soundness case for this algorithm. For the completeness case, so I've assumed that there is some sort of a proof in my tractable fragment from some testable CNF, and here I add this, you know, plus gamma. Okay, so 1 minus epsilon plus gamma testable. Now, what this definition means is, with, you know, this probability 1 minus epsilon plus gamma, when I hit psi with the masked example, right, all these clauses of psi are simplifying to the constant true simultaneously. And so what that means is the restriction of this proof in this fragment actually doesn't even mention the clauses of psi after I hit it with the restriction. Right? It just all drops out. And so in this case, you know, with this high probability, there is actually a proof of the restriction of phi. Okay, and so then with high probability in a 1 minus epsilon fraction, I actually find proofs of the restrictions of phi because, you know, these are proofs in my tractable fragment. Well, so the definition of testable was that there's this, you know, this local simplification rule, right? They're all simplifying to the constant true. Well, okay. Ultimately, there's that AND gate at the bottom, right? You know, so all these clauses up here. With an AND gate at the bottom, and the AND gate only locally simplifies if all of its inputs are true. So only if all the individual clauses are simplifying to true directly. Right.
So can't you just say that, I mean, I'm not sure if this is the way you use the testable formula style. Can't you equivalently say that in your distribution of restricted examples,
Mm-hmm.
Phi follows from Nelson. Phi is tractable, Phi tractable. It's equivalent, right?
True. I mean,
Phi exists.
ultimately,
but phi plays no role. We live in a world that is built from our examples. In these examples,
yeah, phi is always true.
Problem phi, whether it's true or not, is just dependent on whether it follows from no assumption.
Right. So I have, yes. But in general, if you don't have some sort of a promise like the existence of a small proof, this problem is still hard. That's. I'll go there. I'll go there shortly. So.
Sorry, if you want to.
Yeah. So it's another. Again, it's another 30 seconds ahead. Okay. I just wanted to mention briefly before I get there. The same technique works for tractable fragments of many other proof systems. In each case, you just are verifying that restrictions are proving this syntactic form that makes them tractable to search. And these are what Beam-Katz and Soberwell called natural tractable fragments. Okay. So the punchline of this first part of the talk was that simultaneous reasoning and learning these testable formulas from partial information was no harder than just classical reasoning in all these natural tractable fragments. Which raises the question of, well, okay, if it's almost always not harder, could it ever be easier? And that's where I wanted to go in this last part. So I need to, I'm going to fix a special case of distributions here. And it's effectively an unsupervised parity learning problem. Okay. So just to remind you, so parity learning is saying I have these label bits that are computed by some parity of the other attributes. Or equivalently, I could say there's just some parity constraint over my examples. And so more generally, I could have many parity constraints. And then I'm saying I'm getting examples that are solutions to this linear system. That is, now if I have like a uniform distribution over these, it's just I have uniform distribution of this affine subspace. And I'm going to call this an affine distribution. So this is an F2 subspace. So these are Boolean examples. And in such a case, I have these many parity constraints, and I could hope to learn to, these are the rules which will be holding over my examples all the time, and those are the things I could hope to learn and reason about. Right. So in particular, these affine distributions can give you hard examples in the following sense. Okay. Unless NP is randomized quasi-polynomial time, you're not going to be able to develop a quasi-polynomial time algorithm that can distinguish for now log squared degree polynomials whether this rule that the polynomial is just 0 is 1 minus epsilon valid for this affine distribution, or at most epsilon valid with for that distribution. Probability 1 minus delta using examples from this biased coin masking process. So this is basically a polynomial query. It's the kind of formula treated by polynomial calculus, okay? And what I'm saying here is that, so I guess this is my response now to you, Avi. So, whether or not this formula is true or not, right, is just some property of the distribution D, okay? And you might hope that, well, with this very simple class of relatively simple class of distributions and this relatively nice kind of information masking, that I could just determine directly whether or not.
Yeah, but you don't allow yourself here what you allowed yourself before, that there is a tractable fraction that proves it from a testable problem. You allowed yourself this before.
Right. Okay. So what I'm saying is that promise is essential. That somehow that there exists a track.
I didn't say it wasn't essential.
Okay. Maybe I misunderstood.
It's equivalent to removing this assumption and saying that in the world determined by our examples, the formula, the query phi follows from no assumption. Because basically the assumption, the restricted examples set all clauses of side to 0. So
yeah.
And you just care about it. Your algorithm only cares about what happens.
Okay, sure.
So
I misunderstood then.
I find it somewhat artificial to add psi and then make it disappear, as opposed to just say that in the restricted settings, in all the restricted settings,
okay.
you have a simple proof, simple from some whatever fragment you choose of psi itself, of
In each of these
itself.
cases, yeah.
Yeah.
I mean, it's true, but on the other hand, so I introduced this formula psi just to be in closer analogy with, the situation in learning, right? Where you actually produce these explicit examples, and then you say, okay, I've learned these rules, and then you then may take those learned rules and then try to do some sort of operations on them once you've got them as a summary of the data. Just this is the way people have been thinking about this problem. And if I say, okay, well, I don't try to learn the rules directly, because obviously in that case, I just let them go. But I can say, well, I can match whatever you could do if you were trying to learn these rules. And so in that sense, it's somehow easier to make this argument. Whereas if I just say, well, in each of these cases, I could maybe verify psi was true, then you might say, well, what does that mean to me?
Yeah, no, it's just not obvious because the definition is complicated. But that's all that happens.
Mm-hmm.
I mean, if you say, yeah, I can raise this psi, which says that the sun never rises in the west.
Yeah.
And every one of your samples kills this rule because it really never rises in the west. And so you're not really using it in the proof.
I'm not. That's right. On the other hand, it would be useful for some applications if I could determine what this psi was. It turns out it would be nice to know. It's hard. It's one of my open problems. And it's hard to do when there are counterexamples, it seems. It's sometimes easier if it's exact, but okay. Anyway, I'm sorry I misunderstood your question earlier. Okay. Right. Well, I needed this thing here to justify why these affine distributions are interesting to look at. Right. So they don't trivialize the problem at all. Well, they don't trivialize the problem, but they'll allow us to do polynomial calculus and resolution more easily. So, right. So in this last part, I'm going to quickly talk about a quasi-polynomial time algorithm for this mu-biased masking and affine distributions for doing essentially the similar trick, distinguishing slightly valid CNFs from CNFs that I can refute using some testable formula and a polynomial size resolution refutation. With high probability. Okay, and the key points here are, so this is a general resolution, DAG-like resolution refutation, not tree-like bounded with whatever, and I can do this in quasi-polynomial time instead of n to the root n time. Okay. So the property of the affine distributions that I'm going to exploit is that they have what I'm going to call a bias gap. Okay. So if I take any tuple of the literals with this distinguished member L star,
Are we in the affine?
affine. Affine distributions are going to have a bias. Yes, ultimately, but not right now. Right now, this is just resolution. Resolution is still over Boolean distributions. Later, I'm going to talk about polynomial calculus, which is only going to talk about Boolean solutions over polynomials from some larger field.
I just want to know what you're solving now. You are solving now this promise problem.
With resolution, CNF.
Either slightly valid or
can be refuted by a highly valid testable.
And in this case, the distribution is affine, and we are erasing
coordinates by tossing this biased coin.
Which is what, just a positive
Constant. 99% if you like. Right, so the affine distributions have these bias gaps. If I condition on some setting of, these other variables, then, okay, well, it may be that this distinguished guy is relatively unbiased. In the case of a uniform distribution, say, for every tuple, this guy is 1/2 balanced, right? It's taking both values of the probability at least 1/2. At the other extreme, given this tuple, a distinguished member condition on the setting of the rest of the variables may be fixed to some value with high probability, and then I'll say this L star is implied by the other tuple. And when there's some sort of a parity constraint, for example, then if this value may be fixed by the rest of these guys. Okay. And so if every tuple is, where these guys occur with non-zero probability is either beta balanced or 1 minus eta implied, then I'll say the distribution has this beta 1 minus eta bias gap. Well, okay, I mean, it's just, I look at arbitrary tuples.
We are in an affine distribution, so it means that we are just
Well,
picking a random point from an affine space.
yeah, and
We
so,
have just some parity constraints.
yeah, you have some parity
Now
constraints.
we fix some literals, so the parity constraints are inherited on the right.
Yes,
Right? So then every bit is either fixed or
ultimately
completely
unbiased.
free.
Yes.
Oh, okay, so you don't need all this beta, it's just
Yeah, so it's 1/2 and 1.
Okay, yeah.
But the result I'll prove will actually hold for these more general bias gap distributions.
Yeah, but in affine
Right. But yeah, and this is the property I want to point out, is that either they're fixed or they're not, or they're totally unbiased. Okay. All right, so the general result, just to state it very quickly, is quasi-polynomial algorithm, still with this mu-biased masking process, but now for this bias gap where beta is constant, and you have 1 minus quasi-polynomially small, distinguishes these somewhat valid polynomial systems from polynomial systems with some additional testable polys, where there's a polynomial calculus resolution refutation. Polynomial calculus is just these either linear combinations or multiplication by indeterminates. Those are your rules of inference. And you have Boolean and complementary axioms, and you want to derive a contradiction that looks like this, -1 = 0. I'm not going to talk much more about polynomial calculus resolution. I just want to give you some idea of what it is. And the point of this is that, for this class of queries, it matches that negative result that I had previously, showing that without the promise it was NP hard. And you really do get a similar speed up here. Like, the fastest algorithm is still this Clegg-Edmonds and Pagliazzo thing, or the fastest known algorithm was. So, that's nice, but it's a little more complicated. There's one idea that I'm not going to be able to tell you about, possibly more. So I'm just doing this resolution thing right now, okay, which is you can think of as a special case. Good. So just to say very quickly why this happens, let's think about the uniform distribution where there's no parity constraints.
You can just go back to the slide.
Oh, yeah?
What is phi here?
Oh, so phi is your query CNF.
Oh, I see. Oh, but I mean, okay. I'm sorry, I don't know what's the name of the other letter.
Psi.
Oh, psi. So why can't psi just be false? Oh, because it has to be tested
Testable.
on the, oh, I see.
Okay, so to warm up on the uniform distribution. Right, so now these are just, all my bits are uniform. So, right, wide clauses are testable. I think since all the attributes are independent in both the distribution and the masking, I can think about just revealing them one at a time. And each one is some constant probability that it's going to kill the entire clause. So once you reach some logarithmic width, you have a high probability of just being satisfied, or just simplifying to true. Okay, so for the uniform case, basically this theorem would just reduce to using that width-based algorithm in that basic algorithm I had previously. Because when you plug in a restriction, with high probability, all the wide clauses just drop out of that proof, and you're left with something of logarithmic width. And so by doing that dynamic programming algorithm over logarithmic width clauses, if there was originally some sort of larger resolution refutation, you find whatever logarithmic width portion of it survives. Okay, so then you still have some sort of a small refutation. Great. So now for affine distributions, we can generalize that first part of the argument about the uniform distribution. So if we think about wide clauses of our proof where there's a sufficiently wide subclause where, say, there's only balanced tuples. If my clause is, well, is L, or of L star and L1 through Lk, if I look at these tuples corresponding to the clause, if they're all balanced, then I end up with a 1 minus gamma testable clause, and it's basically the same argument. Okay? And actually, if in my implied subclauses, these L stars, that it appears positively in the clause, are being fixed to true if the rest are false, then in some sense, this is only giving you a higher probability of the clause being, satisfied, seen satisfied, and therefore just dying off. Okay.
This is all in the assumed short resolution.
Well, I'm just talking about an arbitrary clause here. Okay. I will use it in the assumed resolution proof, yes. And so in that proof, the only interesting case is going to be these wide clauses where every sufficiently wide subclause contains, some tuple like this, where this L star is being fixed to 0, where the variable is being biased to be false, right? Because then those won't kill the clause. Okay, so I can always find some narrow clause where that thing is being fixed to false, or that member is being fixed to false, and then if I flip its polarity, I get some perfectly valid clause that's narrow. And if I had that, I could use it with a cut rule to eliminate L star, because the rest of this is just a subclause, so it has the effect of just deleting L star from the overall thing. And I claim we can learn these narrow clauses by looking at examples where they're unmasked, because it's log width, and so it's simultaneously unmasked with polynomial probability. So I can directly estimate the validity of these narrow clauses from examples, right? Because in particular, the mask is independent of the underlying example for this mu biased coin thing. And so it gives me a direct estimate of that probability the clause is satisfied. Okay. In this kind of learning setup, there's always some error, potentially. And so I have to make sure that's some quasi-polynomially small thing so that my conjunction of all log n width clauses is still highly valid. I'm losing this little gamma. Okay. Right, so the algorithm is just learning all these narrow clauses by looking at examples where they're unmasked, greedily eliminates literals from the input query, and then searches for narrow refutations of the query using these additional clauses, as some auxiliary background knowledge. I'm probably running out of time here. Yeah, so why is there a narrow refutation? Well, you start with your DAG-like refutation again. If you plug in a partial example from this, masked affine distribution, it's no longer the case that all the wide clauses die, but what's true is that the surviving wide clauses, in all their narrow subclauses, must have some literal that's biased to false. Okay. So now, supposing inductively that the two input clauses here are narrow, are some like logarithmic width, where C log n is this threshold for a clause having some member that's biased to false. Then if you simulate that resolution step, then this next thing might go up to width 2C log n, and obviously we can't repeat that because otherwise this width will blow up. So we'll see how to get it back down to clause width C log n. Okay. Right, so in all of its narrow subclauses, there's some member that's being biased to false. And so I have some sort of a perfectly valid narrow clause which has the negation of that literal in it. And I can use it, because this is one of the things I learned explicitly and provided as additional input to my algorithm. I can use it to just delete, this first L star from that clause. And because it's true for all subclauses of the original clause here, I can continually greedily just find new literals to delete until I get back down to width C log n. Right. So overall, now there's a refutation from these learn clauses and the original input clauses of width 2 times this C log n threshold for the existence of these things that are biased to 0. Okay. This is the richer version of it. Basically, the same ideas give you this algorithm for polynomial calculus with resolution. The only thing that's missing is that effectively, where you're deleting these literals, it's like doing some sort of a reduction modulo the ideal spanned by these monomial constraints you've got, and basically the multiplication rule might mess up the which monomials you get, might change what the reduction order should have been, and so you just need an additional lemma saying you can convert from one to the other. Okay, it's in a paper which I've referenced to at the end if you care. Okay, just to wrap up. PAC Semantics was capturing the utility of these learnable rules of thumb and logical reasoning. For these natural tractable fragments of proof systems, reasoning from these learned premises was not posing any extra cost. And for some proof systems, sometimes the complexity may even improve under PAC Semantics. Right. I promised some open problems. Right. The first one was, can you find these psi's? For some fragments, if there is a perfectly valid psi, it's actually not too hard, given some additional definition, to find a 1 minus epsilon valid psi prime. So really, this is mostly interesting when the initial premise that's that you would use to prove your query is actually itself not totally perfectly valid. Okay, but that that seems kind of hard. I just want to point out that using our basic algorithm where you find proofs for each of these restrictions, okay, this feels kind of like this restriction access learning of decision trees, say, if they're tree-like resolution proofs. The main difference is that for restriction access, you were getting restrictions of the same decision tree, and that seemed kind of crucial for being able to build the tree up. Whereas here, we're just getting tree-like proofs of different restrictions.
You're not trying to learn, you're just trying to validate. There it was a learning problem.
Well, here I'm saying I actually want to find some set of premises psi.
Oh, this is the learning problem.
This is yeah. And I'm saying I'd like to somehow stitch these proofs together and identify some small set of psi's that completes a proof. Okay, so that seems interesting. And yeah, then the second class of open problems is just improving these results in every way possible. Could this bias gap restriction be generalized to arbitrary distributions? Could you weaken this assumption of this biased coin masking process to, for example, merely masks that are not correlated with the underlying example? It seems like you need some sort of lack of correlation because otherwise, you have to reason about the settings, adversarial settings of the underlying variables, and that feels more like some sort of worst case reasoning. And finally, we had this theorem for not just for resolution but for polynomial calculus with resolution. And so it's natural to ask if you could find analogs of it for cutting planes or KDNF resolution. And cutting planes are very natural from a learning theory perspective, so there may be some reason to hope. Okay, that's it.